everybody, this is Henry, and I take these notes really well. I look really funny.
What an exciting way to start our notes. Thank you, Henry Adams. Let's dive right into 5.9 proportions. Check out your learning targets. Obviously, you should be identifying any questions about the notes that you're reviewing. You should be able to both write a proportion and then find an unknown quantity in a proportion using the mean extremes property and using other multiplication relationships. So we've got a toolkit here. Our toolkit includes the means extremes property, which relates two equal fractions to a special multiplication. If a over b equals c over d, then a times d is equal to b times c. Some people call this cross multiplying. As a warm-up or review, please take a few moments to answer each of these questions. Hopefully in number 1, you have found that the cost for 7 baseballs would be $17.50. Hopefully in number 2, you have found that the time that it would take the bus to travel 6 miles is 40 minutes. And in number 3, hopefully you have found that the value of x that makes this a true statement is 6. What is a proportion? A proportion is a statement that two ratios or fractions are equal or equivalent. An example of that would be our final warm-up question is 3/8 is equal to 6/16. It can be stated a little bit differently. We can say 4 is to 8 as 3 is to blank. The relationship that we're talking about comparing 4 and 8 is always a multiplication relationship in some way. It never involves addition or subtraction. So taking a look, how can we compare 4 and 8? Well, we could compare them as fractions. 4 to 8 is equal to 3 to n. And we can look for several different multiplication relationships. For instance, we could look at how are the numerators and the denominators related. For example, the denominator here is double the numerator, or the numerator is half the denominator, which would tell us that n then is 6. We can also talk about how are the fractions related. If I could say, well, this fraction is 2 times the other fraction, we could find some comparisons between the fractions. We can also talk about how we can use the means extremes property to help us. Since we know from the means extremes property, if we have two equal fractions, that we can multiply one of the numerators times the opposite denominator, and that would be equal to the other numerator multiplied by the opposite denominator. So in this particular instance, the means extremes property, using the proportion, we would notice that 4 times, that should be an n. 4 times n is equal to 8 times 3, or that 4 times n, or 4x, in our equation here is equal to 24, which if we solve it by division comes out to tell us that x equals 6. So the means extremes property is something that will always work, but sometimes it's kind of handy to look at those other relationships so that you don't always have to go to the means extremes property. Sometimes the means extremes property gives you some pretty large numbers that maybe you would rather not deal with. So taking a look, give this one a shot. 5 is to 15 as 9 is to blank. You might be able to find the blank just by looking at the relationship of 5 and 15, or even at the relationship between 5 and 9. When we look at these relationships, the order really matters. So we can look at the first pair and try and compare the second pair in the same way, or we can look at the first number to the first number, and therefore the second number to the second number. There's a lot of different ways that we could look at it. So how does 5 go to 15? Well, it would be 5 times 3. So that would mean that 9 is to 27, or 9 times 3. If we want to use the means extremes property, we just set it up. 5 over 15 equals 9 over n, which would tell us that 5 times n is equal to 15 times 9, or 5n equals 135. Solving by division, we find out that n equals 27. Okay, for some reason we saw that example again. Let's take a look at this one. A survey of 200 high school students found that 145 of them had their own television set. Based on the results of the survey, how many students in a school of 3,175 have their own television set? So we need to decide what relates to what. Keep in mind that order is really important. You have to pick an order and stick with it. So at this point, I'm going to ask you to try and determine the relationships involved with this on your own. So press pause, take a moment to do it. And we'll take a look at a few different options after you've tried it on your own first. So there are a lot of different ways to do this. We're going to actually consider two options. If you have a different option, we can discuss it in class just to make sure it is a valid one. One way would be to compare the total student ratios to just those with a television ratio. So what do we mean by that? The sample total is a 200 compared with the whole school total, which is 3,175. So we're comparing the sample total students to the school total students. And we're going to compare that with the relationship the sample television owners to the school television owners. So 200 is to 3,175 as 145 is to blank. We can set up a proportion, the actual statement of equal fractions, and we can use the means extremes property to solve it out. Obviously, there are other ways to do it. We could find what do I have to multiply 200 by to get 3,175? What do I have to multiply 200 by to get 145? I'm going to use the means extremes property because it will always work out for me. So I'm going to go ahead and multiply 200 times n and also multiply 3,175 by 145. After we multiply that out, we do come up with 200n equals 460,375, which is a pretty big number. Divide that by 200 to find out that n is equal to 2,301.875. Now, n here was determining the number of students that do have their own television set. One thing that I do want to double check is that number is smaller than the total students, because if there are more people having a TV than there are people, then something weird happened. And we kind of just want to check to see if it's reasonable. Does that seem like it compares to the total the same way that 145 does? Seems pretty reasonable. If we take a look at another way to do it, we could compare a survey ratio to a total ratio. For example, I could compare the TV owners in the survey to 200, the total people in the survey, as the TV owners in the school compared to the total students in the school. So taking a look here, we could set up a proportion. 145 out of 200 is equal to n out of 3,175. We would use our means extremes for multiplication purposes. And interestingly enough, we come up with the same numbers. Even though we started out with a different relationship, we do come up with the same numbers, coming out at n being equal to 2,301. Or in this case, we'd probably round up to about 2,302 students. In another example, we have a proportion, just a straight up proportion, no problem related to it, situation related to it, where we're asked to solve for h. A couple different ways that we could do it. This one will always work, where we use our means extremes property. And we write the proportion. We use the means extremes property to multiply. In this case, we're multiplying the 2h plus 1, and it's the whole thing, so you'll notice we put it in parentheses, with the opposite denominator of 15, and that's equal to 7h times its opposite denominator, which is 5. We're going to use our distributive property to multiply. We find out that 30h plus 15 is equal to 35h. We can add negative 30h to both sides to see that 15 is equal to 5h. If we divide by our coefficient, we just found out that 3 is equal to h. There is another way to do it that sometimes works, and in this case it works out really nicely. Try to find a multiplication relationship between fractions or numerator or denominator. Since I don't know either of the numerators, the second option isn't going to work. But I do see a nice relationship from 5 to 15. The second fraction is 3 times the first. 5 times 3 is 15. So what we know is that 3 times the first numerator equals the second numerator. So we can see 3 times the first numerator equals the second numerator. Using our distributive property, 6h plus 3 equals 7. We can add negative 6h to both sides. And at this point, we no longer have a coefficient because it turned into a 1, which becomes invisible. Therefore, we just found out, again, that 3 is equal to h, or that h equals 3. And last but not least, we have an example. 2 runners, Eric and Leslie, competed in a race. Eric's time was 0.8 minutes slower than Leslie's time. Their times were in the ratio of 11 to 10. what was Eric's time? This question is actually kind of tricky, and your textbook, in fact, got it wrong. If we know that Eric's time is slower than Leslie's time, we actually know it's a greater time. It took him longer. So we can look at the ratio here, 11 to 10, and we know that 11 represents Eric's time, whereas 10 represents Leslie's time. So a slower time is a larger number. That's really important here. So let's say that t equals Eric's time. Then Leslie's time is obviously going to have to be equal to t minus that 0.8 minutes. So that means that our 11 is to 10. Eric's time is to Leslie's time, the same as t is to t minus 0.8. So if we write this out as a proportion, it would compare Eric's time to Leslie's time in the given ratio, 11 to 10, as well as in our variable ratio, t for Eric's time and t minus 0.8 for Leslie's time. Multiply using our means extremes. There isn't a very obvious relationship here. Use our distributive property to multiply out. We would add negative 11t to both sides, finding out that negative 8.8 is equal to negative t. If we divide by the coefficient here of negative 1, we find out that 8.8 is equal to t. So Eric's time is 8.8 minutes, meaning Leslie's time is 8 minutes. That's everything for 5.9.